Dad is not around. Because Cici May told me about this conference, and I was up to invite myself, but that was faster, and he did it for me, right? And so I'm pleased to be here. I'm going to talk about the flow around the Slender cylinder, right? That is a topic a little bit off the main topics of this conference, right? But there are some tangents, and I would like to explore them, right? Well, I will first try to give the practical motivation and also some conceptual motivation where I need to do some approximations in the problem. Second, I will place from the start the main objective of this research that is a work in progress, right, that is not finished yet. And 3 and 4, I'm going to comment about the flow around the cylinder and some features of Ginzburg-Landau equation and how they can be fitted together, right? And after that, I'll try to discuss Ginzburg-Landau equation as reduced to Navier-Stokes equations as an asymptotic approximation of Navier-Stokes equation. Well, let me. The main motivation of this research is related with offshore oil production here in Brazil, right? As you know, you have a floating platform, a process plant, and you have cables that unite the platform hull to the sea bottom. And among them, you have the risers that take the oil from the bottom to the hull. And those are structures that they are made by steel because the depth is so high that there is no other way. And so they suffer the action of ocean current, right? And due to the ocean current, you have oscillation, VIV oscillation, orthogonal to the current. And well, here we have the typical scales of the problem, the frequencies of order of the income velocity over the diameters, and from some rough estimates about the cable dynamics that depends on the traction. You can estimate the wave number that is going to be excited by the Struve frequency, the mode number, and from this you conclude, from all this analysis here, that the strain due to the vortex-induced vibration is low compared with the yield strain of the material. And so this is typical of a fatigue problem, right? And also, what is important for the model that comes next is that if you take the typical mode that is excited, that is a very high mode, you are going to see that is a resonant problem in almost 10 modes. That is the frequency. The Struve frequency is going to excite almost 10 modes, and so you cannot use a one-mode model as usual to analyze the VIV excitation. Well, just to give some brief summary of these ideas. So VIV excitation of a riser is not a rupture problem because you are well below the yield extreme. It's a fatigue problem, but several modes are excited simultaneously. Also, the ocean current are not only non-uniform modulus, but also in direction, because you have in the upper part of the ocean, you have a north-south current, the Brazil current, and then the bottom part, you have a south-north current, that's a polar current. That is the ocean current is not only non-uniform in size, in amplitude, but also in direction. And the existing phenomenological models, they are all based on Van der Poel equation, are unfitted to analyze this sort of problem, right? They assume in general one modal citation and uniform current. And so you need to develop a way to analyze this problem, right, without resort to this more empirical basic or phenomenological basic Van der Poel equation. Well, I would like to put here directly the final objective of this research, right? You have on one hand a supercritical Hopf bifurcation that's characterized by the instability of the uniform flow around a circular cylinder at the radius around the 46. And from there on, you have a periodic true dissolution that remains until the boundary layer becomes unstable or becomes turbulent, right? Well, in the other hand, the flow is known to be three-dimensional, right? And it's very hard to do full numerical computation of a 3D flow in this size. And what we are trying to do is to join the supercritical Hopf bifurcation with some ideas of slender body theory, where you take profit of the slenderness of the body and the slow variation in z direction, right? Well, and this coupling between the 2D solution and the 3D solution is going to be made by the Ginzburg-Landau equation with complex coefficients that are here. And as a matter of fact, the final answer is going to be written this way here, and I'm going to explain a little bit this, right? By matching the supercritical Hopf bifurcation analysis, that is asymptotic solution of supercritical Hopf bifurcation in the vicinity of the bifurcation, with the Fourier series that you obtain numerically by solving numerically the 2D problem, right? By matching the two of them, you can obtain this expansion here. That is, here you have the steady state solution. Here you have the average solution, comes from Fourier analysis, and the steady state. That is, the steady problem here is written by making this match between the asymptotic solution and Fourier analysis. The first part is this one. The second part is this one. That is, you have the unstable modes from the stability analysis. And here you have the force harmonic in the Fourier components, times the modulus of the Ginzburg-Landau amplitude equation, times z. This is a term that is going to appear later on to correct the incompressibility to the spanized flow. And these are the remaining terms in Fourier analysis. It should be observed, right, that is, if you have this problem here, this is the Ginzburg-Landau equation, and if you take the 2D solution, that is, you take out this term here, that is the 3D solution, the solution is given by this expression here, AE sigma times C3. C3 is the nonlinear term here, right? And this is equal to the Struve frequency minus the frequency of the unstable mode. So if you place the solution here, you would recover exactly the Fourier, the 2D Fourier expansion of the solution. So what you need to do then is first to convince ourselves that this problem can be described by an equation like this. And second, in practice, to determine this coefficient C3, C1, gamma, and sigma, where sigma comes from the stability analysis, omega comes from stability analysis. And so you need to determine C1, C3, and gamma. C3 is given by this relation. And so you need in reality to know C1 and gamma in this problem. Well, just to give you some overview of the main phenomena that occur in the flow around the cylinder, right? Here you have the curve of the Struhel number, the frequency, in terms of Reynolds number. And if you look to this curve here, this is the 2D solution. And here you have the experimental values of the Struhel frequency. And you see that around 200, Reynolds 200, the actual Struhel curve are displaced from the 2D solution, right? That is, the three-dimensionality starts to place a hole here. Well, Henderson, in a numerical work, right, he detected that at this point, that's Reynolds 188, right, the two-dimensional solution becomes unstable to three-dimensional perturbation, right? And you have here a bichaotic solution that is two branches with different frequencies that can happen simultaneously, right? And from here on, you have a truly chaotic 3D solution, right? And those are the main features of the flow around a cylinder. But there are two things that do not appear in these figures that I'm going to comment next. One is that by a proper arrangement of the boundaries of the cylinder, you can induce parallel and oblique shading and change from one to another, and you have a dynamics here that is very interesting. And second, that although here the distance between the 2D and 3D solution is not very, very high, you are going to see that when take the RMS of the lift force, that the discrepancy is very high. The 3D discrepancy, 3D influence is very high. I would like also just to close this transparency, to say that the 2D solution is not only harmonic, is not only periodic, but also it seems to follow, to be tangent to an asymptote for Reynolds larger than 1,000, right? The 2D solution is going to be our basic to analyze the whole flow. Let me go next to the. Well, here you have what I have said, that is the parallel and oblique shading in the range of Reynolds 80 to 140. Here you have the typical figure of the vortex shading around the circular cylinder. But the line vortex here may be either parallel to the cylinder or inclined to the cylinder. And you can have one or another by changing the boundary condition at the end of the cylinder in this range of Reynolds, right? And what's interesting is the dynamics that you obtain when you change from parallel shading, and then you change the boundary condition and provoke here oblique shading, right? Or when you have oblique shading and change the boundary condition and obtains here parallel shading. Because here you have a typical expansion wave in a gas that is you are smoothly changing from parallel shading to oblique shading. And here you have a sort of compressive wave behavior because you have a sharp transition between oblique and parallel shading with a shock wave front here, right? That can be seen in this figure. Here you have some measures of the frequency and the relative amplitude, right? The amplitude and the frequencies, they are obtained by measuring the velocity, and so they obtain the amplitude and the frequency of the signal. And what's interesting here is that here you have the point A, that is closest to the point where the modification was made. And you see that the frequency follows the frequency of the parallel shading until the information reaches A, and suddenly it goes to the other one, that is the frequency to this oblique incidence, that is this curve here. In point B, it takes more time that this wave front to reach point B, and so we have this transition here. The same one obtains also for the amplitude in A and B, and you can also obtain experimentally the velocity of the shock wave. That's here, it's here. Those are the works by Mankiewicz, Williamson in 1996. Well, another important aspect of the flow around the Slender cylinder is what is called the lift rise, or that was observed experimentally by Norberg in 2003. Well, here you have the RMS of the lift force as a function of the Reynolds number. And it's a very difficult measurement because it's not the integral lift force, but it is the sectional lift forces. So you have to have pressure gauge distributed around the cylinder, right? And the cylinder, they have a very small diameter because you have a small Reynolds number, so you have some scatter here, right? But it's clear, or it's evident, that there is a drop, a sudden drop of this value of RMS. And this has been numerically confirmed because you made a 3D simulation, right, with the spectral method, right, at Reynolds equal to 400, and obtained this green point here for the RMS of CCL. That is really on the average curve of Norberg here. And this is very important to our problem because this is the lift force in this direction. This is exactly the motion that you are interested in, right? And so to explain this fact by Ginzburg-Landau equation would be a very important stuff. Well, the parallel and oblique shading, as I said, they have been studied by Mankiewicz and Whitham. And it's interesting to observe here the following. The Ginzburg-Landau equation has a class of solution that behaves as waves in the span direction. Right? Solutions that has an amplitude A0, a frequency, and a wave number in the span direction of this formula here. These are the oblique incidence. And they are directly related, the angle theta with the wave number k of these waves, right? And the long wave approximation of Ginzburg-Landau equation gives Burg's equation. That is exactly this one. And in this Burg's equation that developed shocks, right? They experimentally they infer the values of C1 and C3. This is not a very easy task, but they have been able more or less to infer these values. And they computed the shock wave in Burg's equation, that they have a standard formulation that is just here, just to reference, right? And they placed it here just to see that it fitted more or less to the experimental values. And also they computed the shock wave velocity, it's just this straight line here, as a function of the inclinations before and after the shock wave, theta plus and theta minus, right? You can see a good adherence between the experimental results and the model by Burg's equation. Some discrepancies on high wave number, what should be expected somewhat, because here you have an approximation, a long wave approximation. But also here, that is, you are comparing experiments that are a little bit difficult to be compared, because you have to infer these values C1, C3, and well, but the fitting was good, right? If you take out these imprecisions, these natural imprecisions in this experimental problem, right? And also it is interesting here in Burke's equation, right? Because the diffusive term is this one here, and turns out to be negative when C1, C3 becomes larger than 1. And this is just the Benjamin-Ferrier instability of the Ginzburg-Landau equation. And it's called Benjamin-Ferrier instability in the literature. Well, more about the Ginzburg-Landau equation. Just to try to fit the Ginzburg-Landau equation to what we observe in the flow around the cylinder, right? Given the Ginzburg-Landau equation, Schreiman, in 92, they made a very extensive numerical evaluation in the dispersion plane C1, C3, right? C1, C3, right? And in the stable part, here you have C1, C3 equal to 1, that is Benjamin-Ferrier stability curve. This part here is the unstable solution. This part here you have the stable solution, right? Here you have what they call the phase turbulence, where you have the phase line almost straight, but with some undulations on it. And here you have the defect cause regime, where you have the amplitude goes to 0 and the phase is not defined in some points here, and so you have this much more mixed solution. And what's interesting here is that you have here in the vicinity of the Benjamin-Ferrier curve, in the vicinity of the curve where the problem becomes unstable, to three-dimensional situation, that the two-dimensional solution becomes unstable to three-dimensional solution, to two-dimensional perturbation. You have here also a bichaotic solution, the region of bichaotic solution, that it is a little bit in the stable part, a little bit in the unstable part. It is this region here. Just to recall, it is in the experimental analysis of the flow around the cylinder, you have a bichaotic region solution also in the vicinity of the threshold point 1.188, right? And so it seems to have some relations here. As about the defect cause regime, we are worried about the fact that you are trying to understand how you could repair by Ginzburg-Landau equation, right, the lift crisis by Norberg, right? If you recall that the RMS of the lift coefficient is proportional to the amplitude of the Ginzburg-Landau equation, right? And if you assume that in the chaotic regime, the Ginzburg-Landau equation is a stationary process, and you can confirm this numerically, right? At least a weak stationarity, right? Then you can deduce that this coefficient, this quotient, behaves in this way as a function of C1 and C3, right? And you assume that the amplitude squared, or the modulus of A, would be somewhere proportional to this coefficient cap square. And it says, indeed, that if C3 is kept constant, but C1 goes to infinity, then this value goes to 1. But if C1 is kept constant and C3 goes to infinity, the modulus goes to 0, right? And it's not very clear here because it's in color, right? But you have here the level curves of A and the C3 C1 curve, and you can see that the modulus here is very small, and it increases here, and it's closer to 1 here, right? And so you can eventually, right, you can possibly in the de facto regime, right, obtain a sharp drop in the in the lift forces, right? Also, just to observe, right, it's not difficult to see that you have a Kolmogorov-like scale in the Ginzburg-Landau equation, and these non-dimensional variables, this corresponds to a wave number of order 1. And here you have the spectrums for several simulations, very few energy above k equal to 1. Well, in synthesis, comparing the two sorts of the flow around the circular cylinder and the qualitative behavior of the Ginzburg-Landau equation. Here depends on the Reynolds number, here depends on the product of C1, C3. One observed that parallel and oblique shading, they can observe it below 140, and it's constant with Ginzburg-Landau equation for C1, C3 below 1. That the 2D flow becomes unstable to 3D perturbation for 188, and in the flow around the cylinder, and for C1, C3 equal to 1 for Ginzburg-Landau equation. And it becomes chaotic in this region. becomes bichaotic in the vicinity of these points, vicinity of this curve, and the vicinity of this point here of the Reynolds number, 188. And becomes chaotic above these points, and you have a lift crisis, or you can have a lift crisis also above this point. And so one eventually could fit a curve here, C1 and C3, as a function of Reynolds, that would fit some of these properties. But this is not our intention here. Our intention here is to obtain the Ginzburg-Landau equation as an asymptotic approximation for the flow around a Slender cylinder. And this can indeed be done. I'm going just to glaze over the main aspects here, right? Here you have the periodic to the discrete model, finite element discretized, right, of the flow, the 2D flow around the cylinder. This one you must compute numerically. I recall that the intention here is to obtain to 3D flow based on the 2D solution. What's the basic idea of the Slender body theory is, right? Here you have the harmonic decomposition, the 3 forces harmonic of the solution in its Fourier series, right, until the Reynolds 1000. And you can see that also the components, they start to go to an asymptote, right, around the Reynolds 1000. And so I believe that it's going to continue in this way from there on. But we didn't check yet this numerically, right? This is just to recall that you have the same sort of behavior when you have the lift force coefficient, the Struhel number as a function of number of Reynolds. But the figure is also not very good here, right? Well, if you have the solution and you have the modes, you can now define a finite dimensional and a very restricted subspace made by these modes. That is a basis that is made by the average for the first mode by some few modes here. I would say the 7, 8 modes. So you have a subspace of at most 20, 21 degrees of freedom, right? And this is a subspace of discrete solenoidal space that you have originally, right? And if you project this equation in this subspace, I know that our solution is here. And that this equation has also a steady state, that this steady state is unstable. It's going to look to the limit cycle that this solution projects here. And from this analysis, you can obtain the mode, you can obtain the steady state, the mode, and the pressure mode. Well, the three-dimensionality in the Ginzburg-Landau equation can be easily inferred if you understand that the vortex emission in each cross-section, right, should be out of phase in the span-wise direction if the span is large enough, right? There is a lack of correlation among the vortices along the span. And so, the amplitude that in two dimensions depends only on time, now depends on z and time, right? And you have here to be of the same order of the other components here, that you have a slow variation in z direction that's proportional to the square root of sigma, that is the unstable coefficient, right? And if you go to the pressure expression, you see that to leading order, you are going to have a gradient of pressure due to the unstable mode that's here. And this gives rise to a velocity that's proportional to the first derivative of the amplitude. And from mass conservation, you have a 2D flow that should be proportional to the second derivative of the amplitude. And this gives rise just to the Ginzburg coefficient in Ginzburg-Landau equation. In synthesis, you have you solve b-dimensionally the two-dimensional problem. You solve numerically the two-dimensional problem. You obtain the Fourier series. From the Fourier series, you define some few modes. The subspace from subspace of the solenoidal subspace, right? In this subspace, I made the stability analysis. I compute then the span-wise velocity, and by mass conservation, I compute this field UG that compensates the 2D mass conservation, right? And from this, you obtain the Ginzburg coefficient, because you have also the adjoint mode, right? You compute the Ginzburg coefficient, and from this you obtain an asymptotic expansion, right, of the Ginzburg-Landau equation. And this is indeed the intention of our work here, is to try to obtain numerically, right, these coefficients here, and so to check whether or not all these speculative, but likely, in my point of view, hypotheses are fulfilled or not. Well, the final objective is the coupled fluid structure model, is to obtain then a description of the Heiser's dynamics. You have to discretize the Heiser dynamics along its span by the elastic vibration. And also all the fluid mechanics information is also obtained by discretizing the Ginzburg-Landau equation in the same span-wise direction, right? And you have some coupling that has been already derived, but I didn't place here, right? Between the motion and the flow that synthesizes here, right? And from this coupling, you could then obtain the whole solution, an approximated solution, at least a syntactic solution, of the flow around the cylinder, incorporating the structure dynamics. Oh, those are the reference. That's it.
Questions?